I would like to begin with a confession. I'm a bit nervous to follow the last talk because for a second there I thought I would have nothing to say. There is going to be a very big intersection. I think the aims of our talks are very different, which I'm glad, but there will be a big intersection because I have chosen sort of the same bit and work of Grothendieck as Reading. So I'm sorry about that, but hopefully you'll get to see sort of two ways of looking at that part of Grothendieck. This is work in progress. I have to say that. And it's the first part of what I would like to do with what I would like to do with this study. And to be able to precise this, let me begin. It's been a long time since I become interested in understanding the role of counterexamples and pathological objects, and I take the word object here very lightly. So just anything that's pathological in mathematics with no ontological engagement. And so the work I will present here forms part of this larger project. And I want to, in this talk, sort of work my way through from Grothendieck, a conjecture he makes, to a counterexample that is given 30 years later. So that's the aim of my talk. I don't know if you can read it. When I was preparing the talk, I visited the Chapman website for this conference, and it's underlined in blue. That's my underlining, but it says something like, from about 1954 to 1970, Grothendieck revolutionized algebraic geometry. And it is exactly that period which I will not be talking about. So it is prior to 1954. I just found that sort of funny to read because I thought I would have nothing to say about that. It is exactly from 1949 to 1953 that I will be talking about. And then I make a big leap to 1983, and I'll talk about this year. But okay, so let's get started. First, I would like to make a couple of general remarks about how people see Grothendieck's mathematical ability. The first remark I take from a biographical essay that was published in 2004 in the notices of the AMS. Alan Jackson writes that he had an extremely powerful, almost otherworldly, ability of abstraction that allowed him to see problems in a highly general context, and he used this ability with exquisite precision. And then went on to say that the trend towards increased generality and abstraction, which can be seen across the whole field since the middle of the 20th century, is due in no small part to Grothendieck's influence. So this has been mentioned quite a few times today and yesterday, this sort of like ability of his to generalize. And it was even mentioned yesterday that it wasn't a generalization, it was just like the way he thought of things that was already at a high level. It's not like he was working upwards, that he just sort of began at a very high level.
Sorry, I suppose that is 2014, because you use had.
Yes, that is probably my mistake. But I can't guarantee. Yes, that is a year.
Something that you say or something.
Yeah.
No more alive.
Yes, but what I don't know is if I got the date
That's
wrong.
not so important.
Yeah.
The point is the same in any case.
Yeah, but both is correct. But yes, the year is very likely wrong. Thank you, Martha. And this is going back a bit. The date is not in American format. I'm sorry about that. It's a lecture dated in the 14th of June of '83 from Grothendieck to Ronnie Brown in the UK. And I think it says a lot about one aspect of how Grothendieck grasped and saw mathematics, but it's not actually how he presents his own mathematics. So he says, your idea of writing a frantically speculative, the quotes are his, article on groupoids, it doesn't matter where it's groupoids or whatever, seems to me a very good one. It is the kind of thing which has traditionally been lacking in mathematics since the very beginnings, I feel, which is one big drawback in comparison to all other sciences, as far as I know. Of course, no creative mathematician can afford not to speculate, namely, to do more or less daring guesswork as an indispensable source of inspiration. The trouble is that, in obedience to a stern tradition, almost nothing of this appears in writing, and preciously little even in oral communication. So he's saying this, but it's still the tradition within, Grothendieck's mathematics falls within this stern tradition where none of this speculative or creative mathematics appear. No, he appears to arguing in favor of it, but it's not as if he actually does this. But I find it interesting that he said this would be a good thing, and it would be it's something that would be needed. And now, going a bit back, this is taken from the Festschrift. It's Jean Dieudonné, and it's in French, but I'll translate it. So he's talking about Grothendieck, obviously, and he says he arrives in Nancy in October 1949, and at that moment, Delsac, Goldman, Schwartz, and myself, we had organized a seminar about topological vector spaces, a theory that we had worked with, in different directions. The theory of Banach spaces and of duality in those spaces, which is now ancient, had been well understood by 1950. But the theory of locally convex spaces, general locally convex spaces, was only just being started. And we only knew about very particular types. So it seemed convenient to search if there existed general properties that would account for the behavior of these particular spaces. And he goes on to say that he and Dieudonné and Schwartz, they had worked they had begun work on this study, and they had faced a whole bunch of questions that they could not answer. So they thought it would be a good idea to give those to Grothendieck, and we know how this ends. He solved them all within a year. The questions that Schwartz and Dieudonné give to Grothendieck appear at the end of this paper that's called La dualité dans les espaces F et LF, published in 1949. And it begins, they have a little quote at the beginning saying, given a topological vector space E, this is my translation, obviously, we know how to define various different topologies on its dual E prime, the weak topology and the strong topology being the two most important ones. The study of the relation between this topology is still underdeveloped, and our aim in this text is to carry out this study for F spaces and for a more general category of spaces, which we call LF spaces, that can be considered as inductive limits of these spaces. So this is sort of like the framework that within which the open questions given to Grothendieck fall with. And just a very brief chronology, from 1950 to 1951, Grothendieck publishes 5 memoirs in the Counterexamples. The first one is on topological vector spaces. The second one is on duality. Then there's a third one, which I find very interesting, which I won't talk except for a tiny detail. I won't talk about it here, except for a tiny detail, because it has the word pathology in the title. Then the fourth one is again topological vector spaces, and the fifth one is tensor products. So these memoirs appear in 1950, 1951. So very, very quickly he gets to work and he gets things done. here are the actual titles, the full list. This is taken from the festschrift again. And this is what I find, I say, I'm just going to make a comment here, a brief comment about the third one. You know, I'm interested in this stuff, this sort of stuff. And the title is about topological vector spaces and pathologies in the LF spaces. And it's a very short memoir, and the bit dedicated to pathology is actually just one paragraph. But it gives me the impression that he uses the word pathology in a very light sense, sort of different from other uses in mathematical literature. He's just talking about some things that are strange. It's not really things that are sort of very surprising. And this makes sense because, go on. In sort of going with this train of thought for a second, in the same article by Adane and Schwartz in 49, the third section begins, it's called F spaces and LF spaces. And they say that an F space can be defined as one that is locally convex, metrizable, and complete. And they go on to say a bit more. But they have a note here, a footnote, which I find extremely interesting. And what do they say? They sort of say why they choose this definition for an F space. No? So Adane and Schwartz, they say we're sort of staying away a bit, or we're dismissing the terminology used by Banach and the Polish school, that which is more general. They call an F space a space, topological vector space that is metrizable and complete, but not necessarily locally convex. They call an espace de zéro, ce que nous appelle, that which we call an F space. And they argue that they make this difference because if they allow spaces that are not necessarily locally convex, then they have things that are pathological. And again, this is something I want to pursue further, but I get the feeling, just sort of by looking at what the Polish school has done and the examples that they refer to, that they use pathological in a way that is very it's sort of light. It's not really pathological as other uses of the word have been. But well, that's one sort of thing, as I say, this is work in progress, that I want to pursue. And because I find it very interesting, I find the relationship between the pathological and counterexamples sort of very interesting. And there is no idea, no notion that what I will eventually get to is pathological in any sense. So this is just a parenthesis, and coming back to Grothendieck's memoirs, this is the fourth one. I left the date up here so you could see it. This all happens very fast. This is the 15th of October 1951, and he says by the end of the first paragraph that all the questions that were open in the article by Adane and Schwartz, the dualité, they are now solved. So it all happens very, very fast. And well, this is 1951, and as it has been mentioned, I won't go into detail about this. His doctoral dissertation is published in 1955. He gets the degree in 1953, and with a thesis on tensor products and nuclear spaces. And again, I don't want to go into detail with this. It's just very interesting. This is a report written by Schwartz on the thesis. I'll leave you to read it. I find it's very interesting to read, but I don't want to get into the details. And now, I've been talking about, and we've been talking about topological vector spaces and duality and weak topologies. And I want to go into detail within Grothendieck's work, how he sort of builds a few concepts. So I thought it would be necessary to establish some basic notation, because I won't be changing it to modern notation, and it's quite Grothendieck's work, his definition, his notation, I find it quite heavy. So I think it's better if we sort of agree upon the use of the words and different notations. So he usually works with the space E, and E prime is the dual. So that's all linear continuous forms defined on E that go into the scalar field. And he emphasizes sometimes which topology he's going to give to a certain space. So when he uses a B, that will be the strong topology that is given by bounded sets. When he uses an S, this will be the weak topology. And I mean, it's no different. It's sort of, it takes getting used to. So, because this would be the dual with the topology we would call the weak topology. And this notation is also used. It's not particularly interesting to sort of make a distinction right now for me, but this is the notation that will appear throughout the definitions we'll be seeing. So I think it's important to be clear about it. And that was just sort of like a quick parenthesis so we agree upon the notation. And this is what I want to get to. So I want to show it to you once. It's difficult to understand if the notation has not been made clear, the concepts have not been defined. This is the conjecture I talk about in the title of my talk. So this is what he says. It's in the second chapter of his thesis, page 47. And I want to sort of, instead of just saying here what each of these symbols mean, I want to sort of go bit by bit, because I think it's, there's quite a bit of work to be done. And the definitions are quite charged, and they're heavy, and they're difficult to read. And I think this has an important bearing on what happens after people read this. And in particular, regarding the conjecture that's stated here, it takes 30 years for people to solve it. But I don't believe that it was 30 years that people were actually working on it day in and day out. I think this was sort of something that took a while for there to be interesting. So I will come back to this. I just wanted to show where we were going. And I also want to note that it is a conjecture as such. Yeah. So theorems 8 and corollaries 1 and 2 suggest such and such conjecture. It's not an open question. He's saying he believes this. Yeah. And again, just to make sure we're sort of on the same page, it was mentioned before, and it has been mentioned throughout the conference. I just wanted to make sure we all know what we're talking about when we talk about the tensor product. So I'll be very brief. But let's say we have 3 linear spaces, and we have the set of all bounded, of all not bounded, bilinear operators from x, y into Z. And the idea is, if this space has, if I have the ability, or I can make this space look like something that is not bilinear, but that is linear. So I'm looking for a space here such that I can identify these two spaces, but instead of having bilinear things, I'll have linear things. So I'm searching for a space, let's say V, that does that. And this space V, the space that works, is what we call the tensor product. So it's this, can we linearize bilinear functions? And yes, that's what the tensor product does. So again, this is sort of very basic. I just want to make sure that we're all sort of on the same page. Another way to look at this is via the universal mapping. So for example, if I have the Cartesian product and all the functions that go into Z, and then I have the tensor product here. Sorry, that's supposed to be O times. Then, well, the universal mapping is what I get here. So this would be, and this is sort of the main thing that Grothendieck will work with throughout his thesis and the resume, and well, both of them. And this is the, it's very important because this is sort of the, well, not sort of, this is exactly the notion that 10 years later, when an analyst coming back to Grothendieck's work, they decide that it is exactly this notion that they have to get rid of to make it accessible. So they want to sort of present, recast maybe all the work that's been done in functional analysis by Grothendieck, but by getting rid of the tensor product because they find it sort of too unfriendly, I'm going to say. And now, sort of, remember, I want to get to the conjecture that appears in chapter 2. And I'll go bit by bit. I'm going to make sort of big jumps. I just want to see, one thing I do have to say about Grothendieck is he is very, very tidy. There is not one single piece of information that is missing. So the first proposition in chapter 1, which is this is the title of the chapter, General Theory of Topological Tensor Products. That I translated. I haven't translated this because I'm being very careful with the language, because I also contend that there are about 3 or 4 different types of languages, and you need to translate between them. And it's not just, I mean, they're logically equivalent, but within mathematical practice, I think it makes a big difference which language you use to express these results in. So the first proposition tells us that if E and F are 2 linear spaces and you have seminorms in them, then there exists only one seminorm that works between these 2 spaces. So this is again the bilinear forms, and this is the linear forms on the tensor product. And what he does is he proves that there is only one of such seminorm, and the next thing he does is he defines them. So the seminorm defined in proposition 1 is what he will call the tensor product of the seminorms alpha and beta. And the tensor product with this norm, he will denote by this. This notation is actually sort of standard today, others are not, but this is what we find in textbooks today. And then again, so he now goes to 2 spaces that are locally convex spaces. And he says that there exists on the tensor product a topology T, which is locally convex, and that there's only one that satisfies this property. Whatever the locally convex space G, whichever one we choose, the canonical isomorphism between this space of bilinear forms and the space of linear forms. So there's only that isomorphism induces one isomorphism between this space and this space. So in particular, if you take the tensor product and the dual, then for this topology, the space of bilinear forms matches the space of bilinear continuous forms on this space. So he's building up sort of like the blocks, the different bricks he needs, and he's going very slowly, step by step. And there's quite a few examples, and it's not that unfriendly to read, but the concepts seem to be quite heavy too. So I mean, he's going step by step, but each step is it feels heavy in nature, I think. Then he again makes a definition. The topology defined in the previous proposition is what will define the projective tensor product, and will be denoted by this symbol here. And this I actually kept Grothendieck's text. This is taken from the memoir published in 1955 by the American Mathematical Society. And I find it, in the previous talk, we had quite a few of these taken from the resume. And I find it very interesting how Grothendieck chooses to underline some words sometimes. The bit I want to sort of underline here is that he claims that it's immediate, it's obvious that the tensor product can be identified with the space of bilinear forms that are continuous on this. So again, this would be the dual with the weak topology and the dual with the weak topology. So he's gotten this far. This space can be identified with the space of bilinear functions on that space. And he now introduces this is definition 5. We're getting towards the end of the first chapter. This is sort of like page 85, 87, if I'm not mistaken. And he introduces this notation here. I don't know if you can see it. I hope you can. It's sort of a tensor product with a double hat. And this is, if you remember, what appears in the conjecture. So what he says is if we have two locally convex spaces, we denote by this the completion of this space given the topology induced by this space. And this B with a little e here is again, the B stands for bilinear, and the E stands for the uniform convergence of equicontinuous parts. So again, the notation is quite heavy, but once we get used to it, it's actually very clear. So, and what he's saying is that this space is actually the completion of this space. So it is then very natural for him to say that this is true. This space is isomorphic to a closed subspace of this space. Yes. So, and this is what he wants. This is the conjecture. You know? If this and this is what both are the concepts that we needed, and he's given us so far that this space is isomorphic to a subspace that is closed in this space. So we can now actually understand the conjecture. Not true. Well, we can, because I won't actually read this. I had included this because this is something we still need. We still need the definition of a nuclear space, but that has been just given to us, so I will assume we all remember it. This is how he defines it in his thesis, actually. And we can read this now and understand each of the terms. So we have two spaces that are locally convex, and such that the l'application naturelle says here, from this space into this space is a topological isomorphism. And then he questions, he conjectures that that necessarily means that E or F are nuclear spaces. And he sort of, what he says next has later implications for people trying to see whether this is true or not, because there are sort of like hidden hints here. And the later authors sort of say, well, this bit is true and this bit is true and this bit is not true. So he gives certain things. Okay? So, well, we can finally read this. And then I want to make a huge jump in time. This is 1953. And this is 1983. It's a paper in Acta Matematica, if I'm not mistaken, by Gilles Pissier. And he says, and I love this, because the first time I read this, it's one of those things that, yes, what he says is true, but it's not immediately true. No? So he says that in his thesis and in his fundamental paper, this is the resume 2, Grothendieck formulated the following conjecture. If two Banach spaces, X and Y, are such that their injective and projective tensor products coincide, then either X or Y must be finite dimensional. And you just read it. It doesn't say that. It does, but it is quite, it's not easy. It's quite a bit of work to get from there to this.
You can? Is it they are equivalent?
Yes.
Yeah.
But again, yes, they're equivalent, but I think it's sort of like it's equivalent if we talk in English and it's equivalent if we talk in Spanish, but they're actually different things. And I think that has a meaning here. And this same year, this is 1983, John publishes another paper. This is the Mathematicianale. And he says, Grothendieck again, conjectured a positive answer to the following question. And he calls it G. And he says, let X and Y be locally convex linear spaces such that the extremal tensor product topologies pi and epsilon coincide on the tensor product. Must then X or Y necessarily be a nuclear space? And you can see that this is afterwards, recently Pissier found an example giving a negative answer. But again, this is published within weeks, months of Pissier's paper. Actually, in the paper by John, Pissier's paper is still not published. He quotes a preprint. So, and again, this sort of seems that it's closer in nature. It might be easier to get from this formulation to this formulation, but they still are very different. And again, they are extremely different from what Grothendieck actually said. And then it's if the next step. So this is sort of like the first part of the work I wanted to do. The next part is obviously to look into the proofs of the existence of these counterexamples, and they are very different indeed. John, for example, he shows that there exist two spaces that satisfy this. No, they're non-nuclear Frechet, and they are Hilbertizable, such that this is true. And this is quite different from what Pissier does, because what Pissier does is he doesn't use two spaces, he uses only one. He shows that there exists an infinite dimensional separable Banach space such that this space, so the injective and the projective tensor product coincide algebraically and topologically. This is what I mean. These are his words. And what I find, and I'll finish with the next slide, what I find very interesting is that PC, and this is a quote from the 83 paper, he says that in the last 10 years, under the impulse of, and he just gives a quote, it's 14, but it's a paper by Linden, Strauss, and Pelsinski, that several significant steps were taken towards the solution of Grothendieck's conjecture. And if you look at that paper by Linden, Strauss, and Pelsinski, which is very famous for many things, one of them is sort of like bringing to opening up Grothendieck's work to sort of like the mathematical analysts of the time. And I don't want to read it all. They give an equivalent formulation of what the previous talk mentioned, the fundamental theorem of the metric theory of tensor product. But what I want to concentrate on is this last bit. They say that the paper of Grothendieck is quite hard to read, and its results are not generally known even to experts in Banach space theory. In fact, by using these results, some problems which were posed by various authors in the last decade can easily be proved. All these considerations persuaded us, so that's the authors, to write this paper in its present form. We do not use here the notion of tensor products. So this is very well known. I mean, they chose not to use tensor products, and that's what made it sort of accessible. But I find it quite ironic that when Pissier quotes them, and he's quoting them to say how the counterexample to Grothendieck's conjecture came about, what he's quoting is actually a text that says that the notion of tensor product is what has been hindering sort of like the progress, even though it's a conjecture on the tensor product of things. So it's though you have to take a huge detour and then come back and prove the conjecture, because the language of tensor product wasn't sort of like the appropriate one or easily accessible enough or friendly enough to develop the theory. And then I just had a final comment. It's this is 2008. It's a book by Distel and et al. And they revisit Grothendieck's resume and they use tensor products. So it's sort of like looking back on the work by Linden, Strauss, and Pelsinski and looking back on Grothendieck, and then sort of realizing that there is, however, some value to keeping tensor products around. So this is 2008. But this is not very well known, I think. It's sort of like the results in this book, they're all known, and they're all just sort of like, it's again, a rewriting of Grothendieck, keeping tensor products, but sort of making it more accessible. And I'll finish with that.
Okay.